What's up? I'm back. I've been recently playing with integrals of this structure, and I found a couple nice results related to the zeta function. So yeah, this video and the next video I'm going to be presenting them, and it should be pretty cool. So those of you dedicated Scrumptious Jimmy fans will recognize this integral as one that I've already solved on this channel like a long time ago. So I will just tell you that this equals 7 zeta 3 over 16 minus pi squared over 8 ln 2. Alright, well that was fun. Thank you guys for watching. It was no, I'm kidding. So the point is obviously, we have an answer, but we're going to do something more with that. So it's kind of strange. You typically don't start off with an answer for your integral, but here's the method. So when I solved this integral on the channel before, I used geometric series, and I complexified sine x. You can actually do the same with Fourier series. It's quite trivial. It's more faster with Fourier series to just get this. It's pretty easy. So now I'm going to solve this a different way, which means I should, in theory, get the same result. But with the method I'm going to use, you actually don't get something that's trivially equal. Of course they will be equal, but it's not tautological anymore. And that will give us a nice result because we'll solve for zeta 3. Well, we won't get a closed form because if I got a closed form, I wouldn't be here, you wouldn't be here. I'm not that good of a mathematician, but still it's going to be something neat. So basically, when I was thinking along the lines of zeta functions and stuff, because that's what I was kind of interested in, well, one of the things that came to my head was I remembered this old integral that I did, and I was like, what if sine x has a product formula, right? So what if we tried using that? Because that tends to come up in zeta related stuff. And here it actually makes a lot of sense to do that because you have sine inside of a logarithm. So when you have a logarithm of a product, you can make that the sum of the logarithms, and then maybe we can pull that sum out of the integral and work from there. I don't think I'm the first one to have done this. I highly doubt I'm the first one to use the product formula in this integral, but I am almost certain you haven't seen the result I'm going to get. If you have, good for you, you're more well-read than I am. But it's still pretty cool, and I did technically come up with it. I came up with the idea to use the infinite product in this by myself, so I'm proud of that. Even though I'm not the first, I'm still happy with my, I guess, strategic thinking. Anyway, without further ado, let's just get into it. So we're going to use the infinite product formula for sine to rewrite this integral. It's bad pi. Oh, I fixed it. So this is going to be x. I don't know if you can hear that lawnmower. If you can, I'm not going to be happy. Okay, so sine can be written as x times the product over k of 1 minus x squared over k squared pi squared. Okay, nice. So this will we'll have to split the logarithm, so this will give us two integrals. This will give us from 0 to pi over 2. Oh, yeah, no, it's fine. I really hope you guys can't hear the lawnmower that my neighbors are using. Okay, then we have x. Oopsie, forgot. Okay, notice that the sum came from pulling out the product of the logarithm as a sum and then switching the sum in the integral. So yeah, I've switched the integral and the sum without justification. You'll see that's a very common pattern on this channel, but nobody cares and neither should you. So anyway, we have these two integrals. This one is trivial to evaluate by hand. It's elementary, so who cares? I'll just tell you that this equals, okay, let's see if I can remember it. Should be pi squared over 8 ln pi over 2. Should be minus pi squared over 16, I think. Yeah, okay. So that's easy stuff. We don't need to concern ourselves with that. Now let's look at this integral. We'll call it I sub k, which this one is actually also elementary. because that was like the point. When with this particular infinite product formula, like the resultant integral we get is one that's actually easy to solve, and then we can figure out how to sum it later. But just being able to recognize that sine x's infinite product formula will give us a sum of integrals that are easy to solve, then that means we might be able to make some serious progress on it. Anyway, so let's look at I sub k. First of all, notice we have this x squared and then an x just multiplied into the function, so that motivates a substitution. So that means I sub k is the same thing as the integral from pi squared over 4, from 0 to pi squared over 4 of this. Okay, and then obviously integration by parts here. So we're going to have x times ln of this from 0 to pi squared over 4. Let me make this pi squared a little bit better. Okay, at 0, the terms are going to go away, so at pi squared over 4, we're just going to have pi squared over 4 ln 1 minus. You plug in pi squared over 4 here, that gives you 1 over 4k squared. Okay, and then we're going to have a minus the integral from 0 to pi squared over 4. We're going to have x over 1 minus x over k squared pi squared. And now by the chain rule, we're going to have a minus 1 come out here, and then a 1 over k squared pi squared here, but that can just multiply into the denominator to give us k squared pi squared minus x dx. Bam. Okay, so this is just going to equal to pi squared over 8 ln 1 minus 1 over 4k squared. And then here we can write this as just 1/2. It's minus 1 plus k squared pi squared over k squared pi squared minus x. Okay, so that's just splitting this, adding and subtracting k squared pi squared. And this will just give us, well, this is just going to give us pi squared over 8 minus pi squared over 8. I mean, it's going to give us minus pi squared over 8. And then we have plus 1/2 of this integral. Okay, and this is obviously just like a difference of logarithms thing. We're going to get a minus because of the minus x we have in the denominator. So this is going to give us k squared pi squared over 2, because the k squared pi squared was a constant. This is ln, and then we're going to have, I'm going to write it as ln of a quotient instead of a difference of logarithms, just because it's easier to see. So at the top bound, this is going to be pi squared over 4. At the bottom bound, that x was 0. So it's like this. Clearly the pi squareds go away, and then we're left with k squared minus 1/4 all over k squared. So that's just going to give us another ln 1 minus 1 over 4k squared. Wow. I don't know if you guys can hear it, but it is really loud. Anyway, so yeah, that's what we got. And now, that's our expression for I sub k. So we're going to plug that into the sum right here. So this is, let's pull out a pi squared over 8, actually, because we'd rather work with whole numbers. This is going to be ln 1 minus 1 over 4k squared minus 1 minus, it's going to be 4k squared now, okay, cool. Okay, so one thing that should immediately make you grimace is seeing this minus 1, just this standalone minus 1 inside of an infinite sum. That should be a major red flag, set off lots of alarms, blah blah blah. We'll deal with it eventually, but for now, let's look at this term. Now, I'm not going to combine these two terms actually, because believe it or not, this sum right here of this term is actually going to converge by itself, so we can just treat that individually. So notice that the sum of ln of this is in fact just the ln of the product of that same expression. And recall how we got 1 over 4k squared. It was from pi squared over 4 over k squared pi squared. Right? And this actually, pi squared over 4 is just pi over 2 quantity squared. Now, this is starting to look a lot like our original product we had for sine of x. So let's actually add a little constant term in here. Let's make it ln of pi over 2 times this, and to keep everything balanced, we subtract ln pi over 2. That's just the same thing we had before. But now notice this is in exactly the same form as this, which means this inner expression is just sine of pi over 2, which is 1. ln of 1 is 0. So this goes away. Now notice, so that means that this sum right here contributes minus ln pi over 2. Now we have it multiplied by pi squared over 8, so that means it gives us minus pi squared over 8 ln pi over 2, which is the negative of this term we have. So in fact, this term right here is going to cancel this term, which is kind of sad. You know, it would have been nice to have something with like ln of pi in the end, but, you know, too much to ask. Okay, so that means we are left with this. Let me erase this. Yeah, I'll just move it. So minus 1 minus 4k squared ln 1 minus 1 over 4k squared. Let me see if the camera is still running. Lovely. Okay, so now we have to actually address the elephant in the room, which is this minus 1. So how we're going to do that is we're actually going to look at the other term, this logarithm. So recall that ln 1 minus x equals, should be the minus sum of that, x to the n over n. Yes, after we re-index it. So, okay, our x here is just 1 over 4k squared, which is obviously going to have magnitude less than 1, so it's valid. So that means we're going to write this as sum from n equals 1 to infinity, or actually there's a minus, so we can put the minus out here. 1 over, it's going to be n times 4, it's a 4, wait, yeah, 4k squared to the n. Okay, so that's what we're going to get from expanding that logarithm. Now, what I want you to notice, let's take the n equals 1 term. At n equals 1, we have 1 over 1 times 4k squared to the 1. So that's just 1 over 4k squared. But we're multiplying by 4k squared out front. So that means the n equals 1 term is actually just positive 1, which exactly cancels out this minus 1 we have out front. So fortunately for us, that minus 1 was only there in spirit. Okay, now let's reindex this again because we'd rather have it start at n equals 1. So that'll give us n plus 1, and then this is going to be 4k squared to the n plus 1, but this plus 1 is going to go away because we have it multiplied out here. Now let's switch the sums. So that means we're going to have minus pi squared over 16 plus pi squared over 8 times the sum from n equals 1 to infinity, and then the sum over k. We're going to have 1 over n plus 1. We can pull out the 4 to the n, and then this is going to be k, or I don't need the parentheses, k to the 2n. Now, these terms are independent of k inside of the k sum. So now we really have the sum from k equals 1 to infinity of 1 over k to the 2n, which we all recognize as zeta of 2n. Very nice. So that's where more zeta function stuff comes in. So that means, in fact, what we end up with is zeta of 2n over 4 to the n times n plus 1. And keep in mind, this solved the same integral that this did, so we can just equate these two. So if we equate those two and then isolate zeta 3, we get zeta 3, let me write it a little bit bigger, equals 2 pi squared over 7 ln 2 minus pi squared over 7 plus 2 pi squared over 7 times our little sum here. Don't need an equals there. Let me see if the thing is still running. Okay, nice. Yeah, so this is actually true. This is a very neat little expression for zeta 3, which I had no idea we could relate an odd zeta function to a sum of even zeta functions. Like, that's really neat. You can also like plug this into like Wolfram Alpha or something, and you'll see they match like decimal wise. So yeah, it's actually very interesting to look at this, because not only do you get this new form for zeta 3, which again I'm sure has been discovered before, but you know, it's new to me. I'm happy that I found the right method to create this little expression, but also it's because you see like a variety of terms here. So, you know, when people talk about zeta 3, there's often like this hypothesis, I don't even know if it's a hypothesis, but like a lot of people suggest that zeta 3 could be like either independent of pi, or it's going to contain some like other transcendental kind of terms, meaning it's not going to follow the same like pi to the n power that the even zeta functions contain. But here, notice that we have like ln2, for example, even just floating around. So maybe the odd zeta functions have something to do with logarithms. And also, I want to like look at this term more carefully. If you guys have ever seen like sums of zeta functions, like series, I mean, if you've seen like, for example, sum from 2 to infinity of zeta n minus 1, like that quantity, like those kinds of sums, all like the sums of either all the zetas or the even zetas or the odd zetas minus 1, all those kind of sums and their cousins, they all, they all end up being just like a rational number, because when you expand it, it just becomes like a telescoping series. So that makes me think that whatever this zeta 2n term contributes in this infinite series is going to be just some like rational number, or probably not anything to do with like pi. And whenever, you know, if you look at this term, we have geometric series where like if you have a rational radius, then you end up getting something rational back. I don't really have any like insight for the n plus 1 term. It's just kind of there. And of course, this is all like very hand wavy. It's not rigorous at all. I'm just saying, like, from my experience and my like pattern recognition abilities, from the intuition I've sort of developed for this stuff, it makes me think that like this sum right here is independent of pi. And if that's the case, then that means pi has degree like no greater than 2 in zeta 3. But who knows, like, for example, when I mentioned that ln2 is here, and maybe that means ln2 is somewhere in whatever closed form may exist for zeta 3, that's not even like guaranteed either, because this series right here could contain some 2 pi squared, like it could contain minus 2 pi squared over 7 ln2 just baked in there somewhere, and I wouldn't know that just from looking at the sum. So all that's to say that like just because you can see a particular term in this result, like, you have to be careful. That doesn't mean that it's going to appear in whatever closed form may exist for this, because this sum could have absolutely anything contained inside it. So you can't draw any conclusions because it's not a fully closed form. But that was just some insight I wanted to add. I thought it was pretty cool. Hopefully you guys like that. And this is a pretty nice result, I'd say, just because you're relating an odd zeta function to a sum of even zeta functions. Next video, I will generalize that integral. Yeah, I thought it was pretty cool. See you next time.